Okay, folks. So we'll study hash function and not really digital signature, but MAC. Okay, I thought we'll cover digital signatures earlier, but now we'll message authentication code we'll cover. Okay, so these are the references. So we'll continue to use notes from University of Berkeley, and also I have taken stuff from this lovely book written by Christopher Parr and Pels. Okay, so this very good book on cryptography if you want to really understand the basic concepts. Okay. So I will suggest you to read this book if you are interested in knowing actually how encryption works and various methods of cryptography, not only encryption. Okay, hashing and many others. Okay, all right. Okay. So yeah, so you can do reading from any of these. It is also a very good book by Mark Stamp. And Stelling's book is a classical book which you can, it's like, complete encyclopedia. A lot of theoretical discussions are there. It's very comprehensive book, but I do follow it once in a while. But I try to follow books which are which gives a lot of industrial use or industrial application written by people from industry. Okay, all right. You can also, if you want, you can also get information about video lectures. There's a lot of good video lectures available. So I've gone through these video lectures of Christopher Parr and Mark Stamp. It's available on YouTube. So today we'll study these things. We'll revise what hash functions are. We'll look at common hash functions. We'll look at, we'll not go into details of hash function implementation. We'll leave you to read it. Then we'll spend some time on message authentication code, primarily on HMAC, if time permits. Okay. So this is where we are in cryptography roadmap. We are still in symmetric key encryption. Okay. And we understand the concept of symmetric key, right? I mean, there are two entities and they want to send a document, okay, which is or message, and with the primary aim of having confidentiality. So we can encrypt the document with some key, and let's assume message is it's received by, say, let's assume it's Alice and Bob, and then Bob receives it and decrypts it using same key and something that he has received, which is say M dash. Okay, when we decrypt it with using same key, we should get the same M which was sent. So we have seen symmetric key encryption. We also looked at various block ciphers, and we have looked at DES and AES. So we had the last class we studied hash functions, right? Okay, so today we'll revise hash functions, and we'll try to get at least concepts of MAC. All right. Okay, so what we have studied about hash function is follows. So of course, hash functions are heavily used in cryptography. Okay, so note that it's different from encryption. So encryption, what we have a text string of say n characters or any string of n characters. Okay, and then we encrypt it by say one of the encryption algorithms, say AES, and it transformed into a string which is almost of the same length. Okay, the whole idea here is not to reduce the length of the message, but to change in the form which is not recoverable in the original form until the key is available. Okay, there's the concept of symmetric encryption. However, we often want signature or digest of a message. Okay, you may have an email Okay, and then we want to create kind of checksum, or we want to create a signature of that, such that if the email is tampered by somebody, say Mallory in between, then the checksum of that or digest of that will not match with the digest that's received. Okay, because tampered message that's received by Bob, when Bob calculates the digest, because the algorithm is known to Bob, then that digest will not match with the digest that was sent by Alice. Okay, that's clear. So it gives a fingerprint of the message, okay, which is nothing but a unique representation of the message. So note that in hash function we don't use keys. In symmetric key encryption we use keys, while hash function is well defined function. This algorithm of hash is known. Okay, so anybody can do this. So given a message M which Alice sends to Bob, okay, so this M she sends message and along with hash of M, a digest, right? Okay, now if, all right, so in the plain form this is the way it will work. Okay, if the Mallory in between changes M to M dash or M2, like M double dash, and then while Mallory does not change HM, okay, then Bob can do this function HM double dash, which is the received message, and if the digest that he gets, if it does not match with HM, then he will know. Okay, so if M double dash doesn't match with HM, then Bob will know that message M has been tampered. Okay, simple. Okay, what's the issue here? Is it foolproof? Authentication foolproof? Because basically we are doing authentication here, right? Because in some sense, sorry, integrity we are checking here, not so integrity of the message is tampered by Bob, sorry, Mallory, then it will be detected by Bob. Okay, all right, so we'll come, so this is not the overall solution, right? By putting a hash of a message is not overall, so we'll look at why. Okay, so hash functions are used in digital signatures, which we'll study possibly after a few classes. Message authentication codes, that we'll study in this class. The storing of passwords we have already studied, right? How passwords are hashed and stored in a directory in case of Linux, right? And all OSs do the same thing. And key derivation. But key derivation is, we'll also study later. Okay. All right. So to revise the concepts, hash function is a function which gives a digest, okay, which is of or hash of a message, which is Z here, which is fixed and small. Fixed means that it's a fixed in size, not, and is small. If the it means that whatever be the message length, like your email could be, for example, 1 MB. Okay, the digest of that or hash of that would be of fixed size, some size. Okay, all right, say it could be, say, 512 bytes, bits, for example. It's just an example. Okay, we'll look at what the different values of Z. Okay, and if you change the email size to 2 MB, then even then the digest is of same size. Okay, when we say fixed, it means that it's of the same fixed size, fixed length. The small means that whatever be the length of the original message, the digest has to be small in comparison. Okay. However, a very important property of this hash function is that output is seemingly random. It means that even if you change one bit of original message, the output or output, that's a digest or hash output, will differ significantly from the previous one. I mean, once you make a one bit change in original message, and that message which was original, if you look at the hash of that and then look at the hash of the change message, you will see huge difference, right? Such that you cannot predict what has been changed. All right. So this is the way it's defined, that we have message of variable length, then we pad it, and then we basically do hash function of that. It's like kind of juicer, and then what we get is fixed size hash value. Fixed length hash value is the right word. Okay. Now theoretical computer science will define it differently. It says that it's a hash function is a lossy compression function. Basically, if you look this bit string size of message, which is very large, and then compressing into a small size. Okay. So this is a message digest. And we can see that because of this, there can be collisions. The whole idea is that have a hash function where collisions are difficult to detect. Okay, that's all. You cannot prevent hash function because you're mapping a large set into a small set. Okay. So only requirement is that it should look random, and we have seen the concept of collision, etc. Okay, so this is all we have studied, and we have seen that important properties are correctness. It means that deterministic. Given one m, and if you hash it, and it gives a value of say z, small z. Okay, and do it next time. Take the same message again and do the same function again. You should again get the same value of output, right? Same output. So this is called deterministic. Now, the time to compute this should not be in hours. Should not be. It should be just few milliseconds. Okay, or maybe hundreds of microseconds. Okay, so it should be efficient. Otherwise, if it's very complex, it takes a lot of time, then nobody will do that. And then all these properties we have already seen, that one VNS, second pre-image resistance, and collision resistance, right? First pre-image, pre-image, second pre-image, and collision resistance. So these three properties we have discussed in detail. Okay. Okay, and of course there has to be unpredictability. Okay, all right. Of course all this we have studied. The usage of hash function is message authentication, message integrity, digital signatures, okay, storing of sparse hashes, message fingerprint, integrity of software distribution. We'll see how. Okay. And time stamping. Okay, all right. Okay, which is also called cryptographic commitment. There is how to prove that you have discovered a secret on earlier date without disclosing the context of the secret. Okay, all right. So we'll not go into all usage of hash function, but we'll look at some of these. We'll surely look at digital signatures, message integrity, and authentication. Storing of password we have already seen. Okay. Okay. So now this is what we say, that what is the motivation of signing long messages, right? Which of course digital signatures we'll study later. But here we are emphasizing the use of hash function. Okay. So now when we want to create a digital signature, which is that it's a signature like you sign on a bank check, right? You say that you give Ravi 1 lakh of rupees and you sign it. Then once you sign it, then you cannot refute it. Okay. So digital signature is same as normal signature. When you send an email with your signature, then you cannot say tomorrow that you have not sent the email, okay, with that content. Okay. All right. So signature, now one way of getting signature is that, you have a message M or message X, let's assume. Okay, and you encrypt it using AES. That is symmetric encryption, right? Or DES, whatever. And then you have a message, say X dash out of it. Now you, of course, I mean, only you know the key and recipient knows key. Okay, then X dash is also a signature of your X, right? Because this is unique. But it does not follow a very important property of signature. Right? Signature, let's assume that you have a document, you have, so for example, lease document. When you buy a house, you have a lease document, which is of say 100 pages. Okay, then what is size of your signature? Size of your signature is very small, maybe 10 characters or 20 characters in a pattern, right? Okay, or in which is unique to you, right? It will occupy very small space compared to 100-page lease document. But if you say that signature of 100-page lease document is also of 100 pages, then that's not what we call signature. So when we do encrypt, take a message and encrypt it, then the size of encrypted document, and we want to use as signature, then as big as message, and that's not acceptable. And then we have to have compression of that message because we want to reduce the size. So this is the original message, then we hash it. Now this hash function is known to everyone. Okay. Okay, so basically you get a pattern which is compressed one. Okay, now of course, and then you use a key to sign this small thing that's available. Okay, so we'll study digital signatures later, but all I wanted to say is the purpose of hash that is being used in digital signature, which we'll study later, is to just compress the original message. Okay, all right. So these are the common hash function that we studied in last class, and MD5, SHA1, SHA2, etc. Something that is in use is SHA2 and SHA3. Okay, all right. And this is how we have, we design in a hash function, right? So we have initial value and then take part of the message, compress it, take the output, take second part of the message, original message, and then which is M2, and then compress it, take this output, and again take input from third part of the message, compress it, and use the input that's coming from earlier compression, and then finally at the end you get compressed one, right? Okay. Of course, you can go through these again. So nowadays we have SHA 224, 256, 384, 512, etc. And something that is in use are all these, right? And Bitcoin uses SHA 256. Okay. Now, if you want to know how SHA is implemented, then you can please go through literature. In fact, you can refer the same book that I've said. And of course, there is SHA-3 now. Okay, Ethereum uses, Ethereum is another Bitcoin, uses SHA-3. Any question up to this point? Hello?
No, sir.
Okay. So you can go through this chart where it compares various hash functions. Which says whether collision found or not found, essentially is broken or not broken. And we'll see that something here that's mainly used nowadays. Okay, this gives a lifetime of popular hash function, and for what lifetime, what duration they were being used. And when collision has been found and people could break it, then they were kind of taken out of usage. Okay. But still you will find many application that use hash functions which are broken. Now, breaking a hash function doesn't mean that we should stop usage of that. It simply said collision has been found, and we can find, but usability remains, because if the finding a collision is very difficult task, it takes hours or days or something. Let's assume even hour, and your application requires very small time compared to this time to break a hash function, then you can still use it. Okay, all right. So how do you implement hash function? That you please read is given in this book, Par and Pelzel. So basically you take string x, okay, and divide this into substrings of 512 bytes, and you do pad it, because the last part of this may not be exactly like 512, so you need to pad it with some bits, but after padding you have 512 bits, okay, and then you give this an input to a compression function, okay, and when after compression you will get output of 160 bits, okay, and then use this input as an input to second round. Take now, instead of x1, x2 is input, then use this previous output and do compress, and do this for 80 rounds. Okay, all right. So this is one way. And so what is the compression function, that you will have to see, you will find out. Okay, all right. So this is how you can actually go through the book. So this is how SHA-1 is implemented. There is various stages, 1, 2, 3, 4, and doing something, shifting, rotating, or whatever of bits. Okay, all right. So you can go through it. Okay, to summarize hash functions, note that hash functions don't use keys. Okay, so it means that given one message, it's not Alice who can find digest of the message. Okay, but Mallory in between can also do that. Okay, and then we have studied its security requirements, like one-wayness, weak collision, and strong collision resistance, right? Hash function in practice, hash function of minimum length 256 is desirable. Okay, all right. Now let's move into message authentication code. So what we have studied is that given one message X or string X, we can do compression of that using hash function, and this and whatever is available, let's assume X dash, is small in size, and it's unique. Unique, we can't say unique because there can be collisions. But given X dash, it's extremely difficult to find out what is the value of X. Okay, so it gives a fingerprint or digest of X. Okay, all right. So that we have studied. Now, what is we are here? So what is now need for Mac? That's what we'll have to look at first, and then we'll have to see how to improve on that. Okay. Okay. So just before we'll come to question of why, few things about Mac function. These are also known as cryptographic checksum or keyed hash function. Note this word keyed. Okay, in Mac, sorry, in hash that we studied just now, hash function, we don't have key, and there's nothing like cryptography there. Although it's used for cryptography, but it's just plain compression function. Okay, but now here we are introducing concept of a key. When there's a concept of key, then that key should be known to this to sender and as well as to recipient, which is, it means that for Alice and Bob. Okay, because we are still studying symmetric encryption. Okay, this is very widely used in practice. So they provide message integrity and authentication. However, they don't provide non-repudiation. We'll see once we studied MAC. Okay, these are symmetric key schemes, and MACs are much faster than digital signatures. Okay, so we'll study digital signatures later. Okay, all right. So question is that why do you use MAC? So let's look at this way. Can Alice protect the integrity of M by simply computing hash of M and sending both M and H of M to Bob? Now Bob can find out that Mallory in between has tampered with message M, provided hash of M, which was calculated by Alice, is not tampered by Mallory. Okay, so if M changes, Bob will detect the change, provided that HM has not changed. What happens if Mallory replaces M with M dash and HM with HM dash? Then Bob has no way to detect tampering. Is it right? So Alice sends M. Okay, in between Mallory intercepts it and converts it into M dash. Okay, and now Alice sends M and also H of M. I'm sorry. Okay, so if Mallory is only able to change M dash, and then what Bob receives is M dash and H of M, then Bob will calculate H of M dash and match it with H of M, and there will be mismatch because M is not as M dash. So Bob will come to know there is a mischief. Now if Mallory also changes, this digest to H of M dash, and what Bob receives is not H of M but H of M dash. So M dash and H of M dash, then Bob has no way, because of when Bob calculates H of M dash and compares with the tag received, then both match. Okay, so there's no way if Mallory in between changes both message and also the tag, okay, or digest. All right, so now we can improve it by use of the key. Now this key is a secret key, only Bob and Alice will know it, so Mallory cannot tamper with the digest. So in order to create digest, we'll not only use compression function but also use a key. Okay, so combination of these, both compression and encryption, we call as a MAC function. All right, okay, so MAC will provide both integrity and authenticity. Okay, all right, and it's also called keyed checksum and tag, which we studied later. So it takes a fixed size secret key, okay, an arbitrary size message, and computes fixed size or fixed length checksum. All right, so it's like this. So here is Alice, and she wants to send something to Bob, and she sends it over insecure channel, so Mallory can intercept it. Okay, so we have a message which can be of any length, and this is fixed size key. Okay, note that this key here and the key that Bob has are the same, both are the same. Okay, Now take this message, use this key and do this MAC function. And now what you send out is both original message here, there, and then MAC output, which you call it tag or T. So we send message and T to Bob. Okay, Bob uses the message. Okay, and then the message received, say M. Okay, and uses this MAC function and gets out of this a T dash. Okay. Okay, in order to use MAC function, this key is used. Okay, so this T dash matches with the T received, the one here that's generated. Okay, then everything is okay. Right? What does it mean? It means that message has not been tampered and both message has come from Alice. Why it has come from Alice? Because only Alice has this key apart from Bob. All right. All right, so Bob will know that message has come from Alice because only Alice apart from him has this key. So it will satisfy two conditions, right? Integrity and authentication. Integrity because message has not been changed. If in between message has been changed, right, then what will happen? In between, say Mallory does not have the key. So if she used some random key to create digest, and then at the end, garbled message or change message is received, and Bob will use original key to find out the value of tag, and of course it will not match with the received tag because Mallory in between does not know the key. Okay, any question?
Sir, can we modify the message without changing the tag?
You can do that. So what will happen? What will Bob do? Bob will look at the message and then apply MAC function and okay, use the key, you know, and then it will get tagged. So what will happen? That tag that Bob will generate, because that tag value also depends on the message, because MAC function works. What is input to MAC function? A key K and message. So the generated tag value will not match with the received tag value, which is unchanged.
So the MAC function also has one-wayness property.
Of course. But here, why one-wayness is important? Is it this property is not coming because of one-wayness. This property is coming largely. Of course, it will have, because we will use internally hash function. But this property is coming because we are using the key. The difference between the, when we earlier case where we have sent just hashed output as a signature or a tag versus keyed output, of course, hashing we are doing it because of compression. Okay, but this property is coming because we are signing it. We are actually encrypting, and that encryption can be done with the original key. Otherwise, Mallory can always assume some key and do encryption, but that will give enough input to Bob that either message has been changed or tag has been changed. It means that, because until key is known to Mallory, whatever digest she creates will not match with the digest created by the Bob. Whatever changes in message and tag. Okay. Are you able to get it?
Yes, sir.
Okay. So this, but does it satisfy non-repudiation? Can Bob claim, or can Alice claim that I have never sent a message and Bob has generated that message? No.
No, sir. Only Alice has the key.
Yeah, only Alice has the key, but Bob also has the key. So Bob could have generated this message by himself, any message. But if Bob goes to the court, suppose Alice has not sent anything, okay, and Bob says I have received a message. He creates a message, sorry, which says that Alice promises to Bob to pay $1,000. Okay, Bob creates it, and he knows the key, and creates MAC of that, attaches to this message, and goes to the code that Alice has sent. What is the proof that Alice has not sent or Alice has sent? There's nothing. In code, Bob cannot prove it because Bob also has the key. Okay, so this MAC satisfies two properties, which is authentication and integrity, but does not satisfy non-repudiation. Okay, is it becoming clear? Think about it.
Yes, sir.
Okay, all right. So MAC function is similar to encryption. MAC function is also not reversible. And MAC function, as you mentioned, is a many-to-one function. Is a compression function. It means that it must use hash inside. Okay. So it provides, and also note that it provides authentication but not confidentiality, because message M we are sending as it is. So in between, Mallory can read that message, right? Okay. All right. Okay, these points we have already discussed. So what is MAC will do? It has three parts. First, generate a key. Okay, Alice will first generate a key, and then do MAC function on the message. Okay, that she wants to send to Bob. Use the key and generate a tag, and this attach this tag to message and send it to Bob. Okay, so what Alice will send? Message M and the tag that she has generated. All right. Okay, all right. Okay. Properties are correctness. It means anytime, so many times Alice creates the same message M, then it should generate same value of the T. That gives a correctness. Okay. Efficiency, it should be efficient. It should not take so much time. Security is it EU CPA safe? Now this is another term. Okay. Okay, we'll just go through details given in the book. This Berkeley's book. All right. So MACs are of course used for many applications in addition to communication, that's over internet. Okay. For example, we can use it on USB flash drive. Okay. So for example, our machine could generate secret key and store MAC of each file somewhere on the flash drive. Okay. And if you give a flash drive to your friend and your friend changes some files in that, you can always find out using this mechanism. Okay, simple. Okay. Yeah, please go through it. It's nothing important. Okay. Same thing. Please go through it. It's something that we have already studied. Okay. Now we'll look at in today's class what are different kinds of MACs. Okay, and then note that MAC uses hash function inside because MAC size of the MAC code or output cannot be as big as that of message. So it has got to have one web function, right? So it has to have hash inside. Now what we are using here, we are using hash function and cryptographic key. What are different ways we can use it? So one way is that you get message M, you put it in a compression function, or which is hash, and then output you do encryption with the key, which is known to both the sender and recipient, and this is signature. Now this is the way it was used earlier. What is the issue in this mechanism? Okay, the one issue in this mechanism is, of course, that it takes a lot of time, complexity. So there is a different ways of doing it, and then people found and how it is easy, then how difficult it is to break it. So these are multiple ways people have looked at it. Okay, so one hash function that is commonly used is called HMAC. So NMAC came earlier, and then HMAC is the later one. So NMAC, please go through this PPT, but we'll briefly discuss it. Okay. Okay. So intuition here is that hash output is unpredictable if you do hash of message and looks random. So let's also hash the key and message together. We are using cryptographic key. Okay, and then message and then hash them together. Unlike what we have thought earlier is first hash the message and use encryption. Okay, so what we are doing here is that we are generating two random n bit keys k1 and k2. Okay, where n is the length of the hashed output. Okay, so we have nmac function as k1 k2 and the message on which we want to do mac. Okay, and the output is hash of k1 and concatenated with output of hash of k2 and m. So first take k2, concatenate it with m, do the hash of that. This output is concatenated with key k1. Okay, so the whole output that you receive, you again hash it. Okay, so there's one way, which is called nmac. All right, so okay, all right, I don't know why. Okay, oh, these are the steps. Okay, just a minute, I will tell you the steps again. Sorry. The steps are as follows. First, calculate k2 and m. Okay, generate key k2 and then message m, and then concatenated both. Okay, then this concatenated result you hash, this one you hash, and then now concatenated with k1, fine, and then hash everything. So this is the one way, and you can create a diagram, circuit for this. Okay, all right. We'll just skip it. And then something that is used is HMAC. It's called HMAC. All right. It's proven to be secure. The basic idea is that the authentic, is that key is hashed together with the message. Note that we are not doing encryption here. Okay, this function that we have seen, there is no encryption, but we are using only in these keys. Okay, same thing here, but instead of 2 keys, we have 1 key and we derive 2 keys out of that. Okay, all right. So this aims at providing integrity and authentication. So it is excellent construction because it combines the benefit of both MAC and underlying hash. Okay, all right. So we can use one of these hash functions, SHA-256, okay, or SHA-3-256, or one of these, right? So why not encryption? That's what we have already discussed, right? Because encryption is not fast compared to hashing. Encryption takes a lot of time. Yeah. And what is the other reason? I mean, this H function, see, everything remains the same. If suppose new version of H function comes, you can easily do modification. Okay, you can replace one hash function with other. All right. And of course, there are some legal reasons also. Okay, just few minutes and we'll close it. So to design objective, when this was designed, is to use without modification of all available hash functions that we discussed earlier. We can simply replace it. Okay, hash functions are available in terms of library, and we should be able to use it. Okay, those libraries. That's one motivation. Okay, so that's the reason it also gives us replaceability. A new version comes, then we can simply replace it, right? I mean, like you don't know what version of library function you are using when you are doing C programming and using some library function, or even say printf. Okay, so it's a design, and the new version is maybe more efficient. You'll come to know without knowing it. Similarly, when you use Mac, new library of hash function you can use without any problem. Okay, all right. And this all hash is a very well-known cryptographic, cryptographic analysis of this. HMAC is easy. All right. So HMAC, we do it this way. Okay, we have we compute key is given key, only one key, which is k. From this we derive 2 keys. Okay, a k dash, sorry. Okay, all right. Okay, we derive a key k dash, not 2 keys, but we derive one key k dash. Essentially, we concatenated it, or if the k is too small, then we add bits to it. Okay, and if it's big, then we reduce it. Okay, so if k is too long, we hash it to n bits, and if it's too short, we pad it with zeros to make it n bits. So now we create a fixed size key from k, which is we call as k dash. Okay, all right, and then the output function is h of, these are 2 functions here, right? Okay, first is that h, look at the one here, second one. So we look at k dash and exclusive OR with IPAD. Okay, this is internal pad. So we'll look at what IPAD is and concatenate it with m and exclusive OR with k dash, and we get this value. Then concatenate it with k dash exclusive OR with OPAD, and then this complete output we hash it. Okay, it's a little confusing. It will become clear once you look at the diagram. Okay, now question is that what is IPAD and OPAD? Okay, All right. Just a minute. Okay. Okay. The iPad and OPAD is nothing but some strings, well-defined string, right? So, for example, OPAD or outer pad is hard-coded byte strings, which is 5C, hex 5C, 5C until the same length of k dash. So repeat 5C and convert, of course, into zeros and ones. 5C, 5C, and once it becomes length of k dash. Okay, and iPad is repeat 3636, which is hex, until it becomes same size of k dash, and k dash size is defined, keys fixed key size, right? Okay, now why we do this you'll have to go into design. Okay, why iPad and OPAD is created with this bit strings? There has to be some design thinking about it, right? So designers chose two different bit patterns, even though they theoretically needed to differ only by one bit. As long as they differed by one bit, then because hash of that could be very different, but still they chose, if you'll have to see the bit patterns of 5C, 5C and 3636, it will be quite different, right? But they chose this. Okay, all right. So now if you look at it, how do you create it? Okay, so first is this outer function that we have created, this one. Okay, you look at iPad, which is nothing but a bit pattern of what we have done just now, forgot. 5C, 5C. Oh, iPad, right? 5C, 5C. Yeah. Oh, OPAD. iPad is 3636. Okay, sorry. So we are here. You look at this pattern 3636. Okay, and exclusive with k dash. Here is shown as k plus. Of course, you can read this as k dash. Exclusive OR, you get this one. Okay, pad it with x. That's what we have done here. Pad it with m. Okay, so sorry. This exclusive OR output is concatenated with m dash. That's what we have done. The exclusive output is concatenated m dash, which is x. Okay, hash it. You get some using some key. Sorry, which initial. I'm so sorry. With the initialization vector. Okay, not key. Where are we using? We are not using key. Okay, and this output again combined with exclusive OR of k dash and OPAD, and then you hash it again as an outermost X function and use some IV function here. All right, IV value. So this is how it's designed. Okay, now of course IV value will be known to everyone because it comes as part of design. All right, so what do we achieve out of this? We are doing compression, or one way we are taking advantage of hash function and also advantage of keys. Okay, which is symmetric key, but instead of doing encryption, we are concatenating key in intelligent way and doing hash of that. Okay, as a result you get a signature, a result a MAC function, not really signature but a unique fingerprint. Okay, and of course it satisfies two properties as we have seen, integrity and authentication. Okay, all right, so this is all for today. Please go through HMAC construction if you want. Okay, so MACs provide integrity, MACs provide authenticity. It does not provide other properties. There is a non-repudiation. All right, so that's all. Any question?
No, sir.
All right, thank you. See you on Wednesday.